In this video, we'll continue to learn about different counting methods by studying ordered arrangements, also known as permutations. As an introductory example, see if you can figure out how many seconds are in 6 weeks. Clearly, it's quite a large number. Is there an efficient way you can write the answer? Pause the video and give it a try. Interestingly, you can answer this question using factorials. 6 weeks, we start there. We can then multiply by the fact that every week has 7 days. So we're looking at 42 days. And then we can look at the fact that every single day has 24 hours. And then we can look at the fact that every hour has 60 minutes. And lastly, we can look at the fact that every minute has 60 seconds. This is where the interesting fact comes from. I can then take this multiplication and say, okay, 24, all right, I'm going to call this 8 times 3. And then 60 right here, I'm going to call this 5 times 4 times 3. And then this 60 right here, I'm going to call it 10 times 6. All right, just kind of start to break it down. Well, let's see if we can do even better here. I see that I've got a factor of 10 in my answer, so I'll start with that. I also see that these two 3's could be put together for a factor of 9. And now maybe you see where this is headed. I see a factor of 8 right here, and then a 7 over there, and a 6, and a 5, and a 4. 7, 6, 5, and a 4. Oh, and there's a 6. That's a 3 times a 2. And of course, I get the 1 for free. So 10 factorial is the number of seconds in 6 weeks. Let's look at a real example. Suppose you wanted to figure out how many different ways you could rearrange all of the letters of my last name. We could think of this as a counting problem. There are 7 different letters, so I can think of it as 7 slots. For the first one, I have 7 independent choices. I could choose the H, the A, the W, K, I, N, or S. But once I choose, I've now reduced it down to 6 choices, and then 5, and then 4, and then 3, and then 2, and then 1. So the number of ways that I can rearrange all of the letters of my last name is 7 factorial, or 5,040 if you want to multiply it all out. This is our very first example of a permutation. In mathematics, a permutation is an ordered arrangement of k objects selected from n distinct objects. So the last problem was a permutation because the letters in my last name were all distinct. I didn't have any duplicate letters, only one H, only one A, only one W, K, I, N, and S. And I was selecting 7 of those letters to rearrange. And so the number of ways to rearrange those letters, according to the formula that we have here for permutations, is 7p7. There's 7 letters. I want to choose all 7 of them and rearrange them. The formula says that I could just do 7 factorial in the numerator and then 7 minus 7 factorial in the denominator. And so that reduces to 7 factorial over 0 factorial. And if you remember, we defined 0 factorial in our first video as 1. And so just 7 factorial, or 5,040. The nice thing about this formula is it shows you the right way to adjust if you don't want to select all the objects. The definition says I'm selecting k objects from a total of n, right? I could pick all n of the objects, as I did in the Hawkins example, or maybe I only want to choose 4, only 4 letters at a time. And then I would instead work out 7p4. Notice that for 7p4, the formula says I should have 7 factorial over 7 minus 4 factorial. which is just 7 factorial over 3 factorial. If you think about it, it makes perfect sense. Say we are still working with my name here, Hawkins, and we're picking 4 letters and rearranging, right? I have 4 choices for the first. I'm sorry, I have 7 choices for the first. I have 6 choices for the second. I have 5 choices for the third, and then I have 4 choices. And 7 times 6 times 5 times 4, well, that cascading multiplication, it got kind of cut off, right? It didn't continue all the way down to 1. We didn't then multiply by 3 and 2 and 1, and that's exactly what my formula says to do. Do 7 factorial and then divide off 3 times 2 times 1. Divide out the 3 times 2 times 1, the 3 factorial at the end, because we only want to choose 4 letters. In this example, we're asked to evaluate and then interpret each of these following permutations. So we begin by recalling our formula for permutations, NPK. This is, again, the number of ways that k objects can be chosen from n distinct objects and then arranged. That's n factorial over the difference factorial. So in our first one, I have an n factorial, and then I have a difference factorial. And of course, that difference simplifies to just n factorial. And anything divided by itself is equal to 1, provided that thing is not 0. And so what we're saying is no matter the n, if you don't select anything, then there's nothing to arrange, and then there's only one way to do the arranging. For the second one, NPN, we have n factorial over the difference factorial, and this time, of course, the difference makes 0. But not just 0, it's 0 factorial, which we defined in the earlier video as 1. So n factorial divided by 1 is just n factorial. And if we interpret that, then we're saying there's n things. If you select all of them, the number of ways they can be rearranged is n factorial. And we already knew that. And the last one, maybe this is the most surprising. If I take n factorial and I divide by the difference, now be careful with the difference here, because it's n minus the quantity n minus 1 factorial. And as we simplify that, we see that we get an n minus n plus 1 factorial. Those n's cancel, and you're just left with a 1 factorial. And 1 factorial, like 0 factorial, is just equal to 1. And so we're left with n factorial. It's an important thing to recognize that for every number n, every natural number n, npn is the same as npn minus 1. And if you think about why that is, it starts to make perfect sense. If there are n objects and I start to arrange them, and I say, oh wait, I'm going to leave the last one out. I'm not going to bother to arrange that last one. Well, in a sense, I already have. You know, it's like putting it at the end of the line is kind of the same as leaving it out. And that's why npn is always equal to npn minus 1. I think there's a little bit of a danger in just thinking about permutations as a formula, which you can plug numbers in and crunch some numbers and figure out an answer. It's important to recognize that the permutation formula is useful to apply to different types of problem-solving strategies. Sometimes it'll be a direct application. Other times, you'll use it as part of a bigger calculation. We'll see that in the next few examples. In this example, we're asked, in how many ways can Arya, Bran, Cersei, Daenerys, and Ilaria sit in a row if Arya and Cersei cannot sit next to each other? To solve this problem, I'm going to use an indirect counting method. Note that the number of ways that they can sit in a row where they don't sit next to each other, I counted all of those, plus the number of ways where they do sit next to each other, don't plus do, that needs to equal the total number of ways, right? And the total number of ways that 5 people can sit in a line is a relatively straightforward calculation. You could either think of it as 5p5, or you could just think of it as 5 factorial. Right? So I know the right-hand side of this equation, and I just have to work out the don't and the do. Well, the don't is what I want to know, so let me just call that x. And when I want to figure out the number of ways that they sit in a row where they do sit next to each other, that's actually a relatively straightforward calculation. Picture it like this. I have 5 people in a row. I'm going to put a bubble around 2 of them because they need to stay together. And so really I have 4 things that I'm arranging. Bran, Daenerys, Ilaria, and then this bubble that contains Arya and Cersei. So 4 things can be arranged in 4 factorial ways, right? However, Arya and Cersei themselves could be arranged in 2 factorial ways. It could go AC or it could go CA. So you have to arrange the 4 and you also have to arrange the bubble. So the total number of ways that these 5 people can sit in a row in which Arya and Cersei are sitting next to each other, well, that's going to be 4 factorial times 2 factorial. So if I put all this together, my answer for x, what I'm looking for here, and how many ways can they sit in a row if the 2 do not sit next to each other, is simply going to be 5 factorial minus 4 factorial times 2 factorial, which is equal to 120 minus 24 times 2, which is equal to 72 ways. Of course, this assumes that you've actually seen Game of Thrones and you know who all these 5 people are. If these are just 5 random people that you can't tell the difference between, then this wouldn't fit the criteria of a permutation, because in a permutation, all the objects need to be distinct. And that brings us to our next definition. Sometimes the objects are not distinct. Sure, people are always distinct. You can tell the difference between one person and another, even if you don't maybe know their name. But sometimes you're arranging things like letters, and I can't tell the difference between one letter L and another letter L. So we have a way to adjust our permutation formula when the objects are non-distinct. A non-distinct permutation is an ordered arrangement of n objects, of which K1 are of one type, K2 are of another type, and so on, all the way up to, say, Km. If you want to figure out the number of arrangements possible for a non-distinct permutation, all you do is you take n factorial and divide out by K1 factorial for all of the ones that are of type 1, and K2 factorial for all the ones that are of type 2, and K3 if there's a third type. There doesn't need to be a third type. Maybe there's only 2 types. But you just keep going for each K sub I, which is representing the number that are of each type. Perhaps this idea of a non-distinct permutation reminds you of a problem that came up at the very beginning of our first video about counting, in which I asked which name, Owen or Lily, could be rearranged in a greater number of ways. The problem doesn't have an immediately clear answer. Owen has fewer letters, which would lend itself to fewer rearrangements. However, while Lily has 5 letters, those L's are non-distinct. You can't tell the difference between them. And thus, that really restricts the amount of rearranging that you can do. For example, in Owen, when I swap the O and the E, I come up with Ewan, a new arrangement. Meanwhile, with Lily, if I swap these 2 L's, it still spells Lily. And that's not a new rearrangement. And so we can answer this question of which name can be rearranged in a greater number of ways using all the letters using what we just learned in that formula. So for Owen, all the letters are distinct. And so his name can be rearranged in just 4 factorial ways, which is 24. If you prefer, you can say it's 4p4, right? All the same thing. Meanwhile, with Lily, the number of rearrangements would be 5 factorial if all the letters were distinct. However, 3 of those letters are type L. So I must divide by 3 factorial. Also, if I care to continue here, one of those letters is type I, and one of those letters is type Y. So I could illustrate all of the different types of letters, the L, the I, and the Y, by putting those 1 factorials in the denominator. Of course, you know, dividing by 1 isn't going to change the computation, but you can do it for illustrative purposes. So when we simplify here, I've got 5 times 4 times 3 factorial over 3 factorial times 1 times 1. The 3 factorials cancel out, and Lily's name can actually only be rearranged in 20 distinguishable ways. So Owen wins that battle. As another example of the non-distinct permutation, we have anagrams. And the famous anagram from Harry Potter is Tom Marvolo Riddle rearranged to I am Lord Voldemort. The question could become, how many different anagrams are there? You know, maybe some of them are complete nonsense of Tom Marvolo Riddle. So to figure out the total number of anagrams, we can use our non-distinct permutation. And so we just count up the total number of letters, which is 16 letters. So it would be 16 factorial if they were all distinct. However, I see that one of them is type T. There's only one T there. 3 of them are type O. So I divide by 3 factorial for the O's. 2 of them are type M. There's only one A there, 1 factorial for the A's. You can leave off the 1s if you'd like. There are 2 R's in that name, so 2 of them are type R. There's 1 V. All right, I already did the 2 O's, 3 O's, I guess. 2 L's. I already did the R's. There's an I, 1 I. There are 2 D's, 2 factorial for the D's. Oh, you get the idea. And then there's 1 E. There's only one thing that I wanted to mention here. If you do include the 1s in the denominator, the nice thing is you can check that you've counted all the types and you didn't miss anything by simply adding all of those numbers in the denominator and making sure that you get 16. 1 plus 3 plus 2. It's 1 plus, yeah, that checks out. That all adds up to 16. That way you make sure you didn't end up double counting something. But writing all those 1s in the denominator is a bit annoying. For our last example today, I'll ask you this question. Imagine there were 7 light switches on the wall. The question is, in how many different ways could you rearrange those light switches so that exactly 2 were on? So how many arrangements are possible with exactly 2 turned on? Think about that. We'll answer it in a couple different ways in our next video.